All right. Hi, everyone, and thanks for joining our data-driven quality assurance webinar. Here, my name is Emil Ackerman. I'm one of the founders in Quva and currently the director of sales and marketing. And then we have the star of the day, Tapio Manninen, our chief technology officer, who will be giving you some of his thoughts on how to solve issues related to quality assurance in manufacturing and production. So you probably see the video now and hear us. I will now shut down the video so that you can concentrate on the slides that Tapio will be presenting you. We will be offering also the replay of the webinar. You will be getting an email 24 hours after this, in which you get the link for watching the webinar again, or then you can forward it to relevant people or colleagues of yours. So Tapio, if you share the screen, and I will turn off the video from here. All right. It's flashing. Can you switch the slide? Okay, so our faces again, well, you saw them already, so let's move on. And I'll just shortly go through what Quva is if you already don't know. So we are a software company focusing especially on the pulp, paper, and cardboard production, but we do have projects and installations also in other industries. We're talking mostly about companies who are collecting a lot of information from their operations in form of data, and they want to be more efficient and want to do things right the first time. Those are kind of a very fruitful environment for what we are doing. So basically, what we are doing is automatically combining data from different sources, analyzing it, refining it into more meaningful information for decision support, and in that way, our customers and the staff in the mills and the factories get relevant information in the right format, in the right time, in the right place, and through that they can perform better. But today we're focusing on the area of quality and quality assurance, and let's move on to that. Tapio, the floor is yours.
Thank you very much. Okay. Thank you, Emil. So, welcome everybody. My name is Tapio Manninen, and like Emil said, I work as the CTO here at Quva. And the topic, like you already know, is data-driven quality assurance. And my talk will be about 30 minutes or something. And after that, Emil will still give you a short wrap-up and conclusion of the webinar. And please let us know if there is any problems in the audio connection or something. You can write in the chat of the webinar application. This is our first time having this kind of heading. But let's go on. So, like I said, we are here today to talk about data-driven quality assurance, and I will be using this kind of simple gauge example to present some ideas that I have on this topic. The kind of basic claim that I have in this webinar is that now that we have all these kind of newly emerging data-driven analytics coming, machine learning, AI, etc. So my claim kind of is that this should only be seen as a logical continuation for these kind of traditional ways that we have been using in quality monitoring and quality assurance. And now that we have been working on this kind of industry for some years now, we have maybe discovered that there is still quite a lot of demystification needed about these kind of new data-driven tools, so that people understand better how we can use them and what's the actual benefit and what is the actual motivation behind this new AI hype that is going on. And well, the motivation is quite simple from our point of view, and this is merely better exploitation of these big data masses that we have now coming from our processes and stored into our databases. So this is the main claim here, and at the end part of the webinar, I will also discuss about some common problems that we have encountered this far when working on this field with these topics this far. But yeah, you see the cases on the screen. Let's go these through a bit more in detail. So the idea is quite simple. So basically the story is such that first we have some kind of real-time monitoring. After that, we are building a specification limit alarming to the monitoring. After that, maybe statistical process monitoring, SPC, statistical process control things that rely more on data. And at the end, if we look at it like this, we see these newly emerging advanced statistical process optimization, big data algorithms as a logical continuation for this kind of application. But let's take a look first at this concept of monitoring. So we have a real-time process here where we are aiming for optimized quality. And well, I will be using examples mainly from the paper making field. That's because, well, that's where Quva mostly works on pulp and paper, and also the audience today is largely from that field. And let's say that we are making paper here, and the quality is to achieve, for example, a certain whiteness level of our end product. And I happen to know that one parameter that is affecting the whiteness is the amount of blue additive. I once learned this in Imatra, I think. So anyways, the first thing that you do is that you, of course, monitor and control the amount of blue color in the process. So with this kind of gauge, simple gauge, you are able to constantly see what is the blue level, and then you can use your process knowledge in order to make actions and to get the desired whiteness level. So this is quite simple idea, and it is quite effective also in many cases, especially in simple processes. But this is, of course, not what we want. There are downsides in these things, and well, the first thing is, of course, that there is a constant human monitoring needed to look at this gauge, and also these operators who look at these gauges, they need special training in order to understand how the blue color affects the whiteness and how it should be controlled. In many cases, this approach is fine, but in our case, we want something more. And the next step here is, of course, to add some kind of alarming limits to the monitoring, to the gauge. So in this case, there has been a process expert who has set the specification limits for the amount of blue. So there is some kind of minimum and maximum limit. And this works as a guideline on what kind of the blue level should be in order to get the desired whiteness level in the end. And And this, of course, then frees us from constantly monitoring the process, so we can have a lot more things to follow and optimize. And this is quite clear after all that you know that maybe the blue level is not the only thing affecting whiteness. So that's why this is a good idea to do like this. I don't know what other might be good things to follow than blue, but maybe the audience knows better than I do. Okay, but let's go on. So the downside in this kind of approach is, of course, that when you need to manually set these alarm limits to all the important things that there is, that it can be require quite a lot of maintaining, and also in most cases that we have encountered, the process is so complicated that the all drivers for this end quality are simply not known. So you are not exactly sure what all things you should monitor in this manner in order to get the best possible whiteness level. So this yet again creates a demand for even more automation and even more data-driven approach into this monitoring application. And the next step is and has been to bring some kind of statistical process monitoring thing into this approach. And here on we start to do things more in a data-driven manner. So in this example, for example, you have a statistical process monitoring, and there are the SPC, statistical process control methods, are used to automatically create these kind of alarm limits. SPC might be the most widely used method, relying on this kind of simple statistics, computing the variance. So we kind of assume that the more variance there is in the process, the worse quality we get. And similar methods as SPC are found also in the field of machine learning. For example, these unsupervised anomaly detection methods and so on. I will soon come back to this machine learning part, but in this context, the main difference, for example, to SPC is that machine learning just tries to exploit historical data better, but that's not relevant yet. So anyways, in fact, SPC is actually one sort of machine learning algorithm because it learns the variance from the brief history in the back. Yeah, but the point here in this slide is that this kind of data-driven approach enables us to further automatize this process controlling. And in this case, that means that we can generate and maintain these alarm limits automatically. And this can already be quite effective, and I think many of our customers are using already this kind of approach, either using Quva's tools or somebody else's tools, but this is basic stuff. So the next question is of course that where can we improve even more? And especially if we are talking about from the viewpoint of quality assurance now. So one thing that we have found out to be quite relevant in this field is now that we are talking about alarms and alarming, is the relevance and quantity of the alarms. So our clients quite often say that they have too many alarms, and especially irrelevant ones. So another thing that this kind of analytics can provide in order to actually improve the quality instead of just notifying when something suspicious is happening. So keeping this in mind, we go to the next gauge, which I call the big data-driven process optimization. So the key idea here in this case is that we now try to exploit better the kind of historical data that we have. So like in SPC, this kind of data-driven approach here is taken in order to automatize certain tasks. So the big emphasis is on historical data however, at this point. So the previous monitoring and the SPC examples, they didn't kind of use the information on how things have been done in the past. Instead, they kind of look at the current process state or short window in the near history, and this way try to improve things. But this kind of big data driven term, I mean that we should also look at the years of historical data that are stored in the databases that we have currently. And with this kind of approach, I see at least two things that we can achieve. So the first thing is that with using the historical data, we are able to see how things have been done in the past. And this kind of allows us to do this kind of automatized mining of tacit knowledge. So tacit knowledge is a big theme among our customers and among the things that we have been doing here at Quva. And we know that there is a lot of important stuff included in tacit knowledge. So that's the first thing that we need to kind of mine, or we are willing to mine from the data that we have. And the second thing that I think that we can achieve with this kind of big data-driven approach is that this would allow us to target more specifically into the problems that we are interested in. So for example, in this paper making case, if you are interested in optimizing whiteness level, we can better target into this area using this data-driven approach. When we compare, for example, to alarming about everything that looks suspicious in the process, like this SPC things. So the key idea here is that now that we have been automatizing these things one by one, the next step is now taken towards automatizing the actual decisions, not only the alarming. This is one thing that could be achieved by this kind of, for example, machine learning methods. And now the interesting part, of course, now is that how is this done in practice? And this is what we are trying to solve every day. And well, I will discuss you about machine learning methods. This is one way to take on this problem. So let's move on. Let's take a concrete example next. So it tries to explain you better how this is done in practice. So here's a factory, and obviously it's a paper factory in this case, and it is manufacturing reels of paper. And in this example case, also let me first before I go to this example is made up real life example. So it could be real life, but I made it up. So in this paper reel manufacturing example, the main idea is that we want to avoid getting quality claims. So that's why we are focusing on quality in our process more than other fields maybe. So that's the #1 priority in the process. And we have a paper factory producing reels of paper, and there are vital quality parameters that we are we are measuring after the process, and let's say that in this case that they are shear strength and square mass, for example. And let's also say that the quality is quite rather hard to measure. I know that in some cases quality measures are done automatically after every paper reel, but let's say that in this case we need to send a sample into lab before we can be sure what was the end shear strength and square mass that we ended up having in our reels of paper. And this kind of sending into the lab is done either periodically every now and then, or maybe every time we think that, oh, okay, now there is something wrong. Anyway, the goal is to catch these quality faults that could potentially end up being claims from the customers. And one big problem in this example case is also that these lab measurements, they can take from hours to even weeks to get ready, and depending on the product type, for example. And also it might be impossible to measure all the reels before we are sending them to the customer. So the question is that how do we avoid these kind of customer quality claims the best way we can, using the available process data that we are collecting and the information that we have from our processes. And secondary, how do we avoid also producing tons of faulty paper while waiting the laboratory results, because it turns out that these faulty paper reels come in a sequence. So in the essence, this paper making process is like a continuous process. So the subsequent reels of paper, they depend on each other in that sense. So how do we avoid faulty paper and quality claims? Okay, so the first thing that we do, of course, is that we add monitoring to the process that we have. We have certain set of critical process parameters that we know based on our knowledge that affect the end shear strength and square mass, and we follow these. And then we make also this kind of alarming that I already discussed about, and even SPC alarms we can trigger on these selected critical process parameters. So now this setup or our manufacturing process, it can automatically create alarms of this kind of excess process variation, and which then are possibly leading into bad quality. And this kind of setup is used widely, I assume, and of course in this case it has already clearly reduced the number of quality claims. But there are a couple of problems still persisting, however. So like we probably, many of you already know, that the formation of quality, it is always a kind of sum of many things to happen. So in many occasions, for example, none of these single variables that we have set as critical parameters, none of these single variables are alarming, but we still get bad quality. And also in majority of these alarms that we get from the process variation, they don't actually result in a declined quality, but they are instead related into some other things. So there are a lot of false alarms, and also some quality claims are missed because the reason behind the claim is not shown by the critical process parameters. So at the end, there's quite a lot of work still left in figuring out that which of these alarms are actually relevant and which should be followed by an action. So our question now at this point is that what's the solution then? And happily, in this example, we have stored all our process and quality data since the last 2 years. And now we have good data scientists working at Quva and together with the factory, and we are actually away. It is possible for us to use the historical data and create a machine learning model in this factory example. And this machine learning model works such that it shows a kind of a risk level, that what's the risk that a newly manufactured paper reel will end up having bad shear strength or square mass. Here's a visualization of that. So we built this cool little machine learning application, and which predicts the shear strength and square mass of each paper reel before we are actually sending them to the lab. And we run our little proof of concept study and find out that there is actually a 50% chance that this machine learning model can actually detect the faulty reel before sending the reel into the lab. And there is, on the other hand, there is still a 50% risk that this kind of alarm given by the model is false. So 50-50 chances in the both directions, false and true alarm rates. The first question that comes to our mind is that it sounds a bit bad, doesn't it? So what do we actually do with this kind of fuzzy alarming system that we cannot rely on? Actually not very well. So, but there the answer is clear. So we do the same thing with this kind of knowledge that we have this far done with the other statistical alarming tools that we have had this far. So we use this information to adjust our quality sampling and also the real inspection routines that we have made this far. So we can more smartly with this kind of, nevertheless that the information is fuzzy, we can use it instead in this kind of smart process control kind of things. And in this happy example here, we were able to, due to this new machine learning online prediction model, we were able to get from each and every row, we were able to get a prediction of the shear strength and square mass. And this paper mill here, it ended up cutting down about 40% of their technical quality claims. And so the factory lived happily ever after. Okay. So I'm not saying that the story is true or false. The learning here, the story here is that the story here is just to show you that how this type of, in this case, machine learning powered inspection system builds on the existing data environment that we have already on the manufacturing line, the measurements and the IT environment and so on. And with this kind of approach, we can bring new insight on these targeted quality problems. So the one main thing in this example was that we were able to specifically look at the shear strength and square mass, which were the most important things. Okay, but this was the kind of concrete example. Next thing is that many people ask that, so what's the kind of problem then in using these cool new methods and big data driven approaches that we are marketing and hyping? So why aren't these methods and applications already used all over the paper world then? So here on the screen you see the Gartner hype curve, and by our knowledge. The main problem is that when looking at these machine learning applications, for example, for applications of quality assurance, especially in heavy industries, the problem is that on the hype curve, we are kind of going down towards, at the moment, towards the valley of the death, so-called valley of the death. And that the main slowdown at the moment is that not too many people see these data-driven approaches like I have presented in this webinar now. So I mean, they don't see them as continuation for the existing quality assurance methods, but instead there are still quite a lot of prejudice, which of course is due to the fact that these methods are not very well known. And another thing is, of course, that no clear benefits have been able to proven yet at this point. So there are not too many success stories at the moment that use machine learning or big data approaches. So maybe quite many companies have of course done something using advanced analytics, and they have had their own proof of concept studies, but in many cases they seem to just give cryptic results that are too far away from these practical applications. So if I, for example, present some cool new things to the CEO, he might say that he might discontinue this kind of data-driven project because there's not commercially sound payback plan provided at this point. And of course, this is quite clear because these projects that we have been traditionally doing now have been quite short, maybe 2-month research studies. So there is still a lot to go before we can actually benefit from these things. The good thing, of course, now is that there's more and more people slowly starting to see the nature of these things, and also we are slowly starting to get these real benefits as well, at least here at Quva. And if Gartner predicts correctly, it will be a year or two before we are past this valley of death, and productive application will start emerging more and more. Okay, but this will be my last slide. So what to actually take away from the message that I have given in this webinar. So why we are doing these things now is partly because we have understood that we have new ways. We have new ways of doing data science. For example, we have these algorithms. Then we have data stored in the databases that we have previously not have had. And then, of course, computational readiness and these kind of things. But what is still kind of relevant to understand, for example, about machine learning, that these tools that we are using, they are not a set of magical tricks. For example, machine learning is essentially just curve fitting. So you have data and you try to fit a model to the data, and then later you can use that model to predict or do whatever things you want. Even better, I would say that machine learning is just finding similar cases in the historical data that you had previously. So basically, if you have a good set of historical data, you can find all the relevant cases of your process in the historical data and use that kind of like tacit knowledge. And another thing to understand is that that these kind of data-driven methods, they are always statistical in essence. So that means that you need to know how to deal with kind of uncertain results. So that's the same thing as with the old statistical tools, SPC or whatever we have used in the past. So these are kind of not new things that we are talking about. And of course, then if we want to exploit these new machine learning, etc., this of course creates this demand for the both computational environment and data that we need to have. So there's certain technological readiness required before we can start playing with these new tools. One example, for example, from the quality prediction would be that if you want to predict quality to the future or the current quality, if you want to predict what kind of quality you are having from your process, then you of course need to have the data that contains this kind of predictive information. This sounds quite simple, but it's not always that simple. And also one thing that I have noticed is that quite many times we are talking about forecasting, which is just a special case of predictive modeling. But it's quite relevant special case, especially in kind of operations where we aim for proactive improvements. For example, preventing bad quality for ever happening in the case. But this forecasting, I have noticed, can create a lot of confusion in the sense that what actually can and cannot be done with these data-driven methods. So, and especially in the Finnish culture where we use the word ennustaminen, the ennustaminen, it means both prediction and forecasting. So that creates even more confusion. I remember about 12 years ago when I was still working at the university, and we implemented first machine learning applications for the Finnish customers, and we started using Finnish terms, and this ennustaminen was one of those terms. And back then it felt strange to use this word because it doesn't we are not thinking that we are doing like forecasting into the future or even prediction, but and back then it felt kind of even cool that okay, this is like looking into a glass ball or something. So that's when we started to use the word ennustaminen. Now if I had the chance, I would have not started. So today I'm cursing the word ennustaminen. Okay, but that's the story back then. We don't need to go to the term AI. That you already know that AI is just mainly used as a liberal marketing term, but although it of course has a technical meaning as well. Okay, but this was my take on this data-driven quality assurance theme, and I hope you had some new ideas to take away with you after this. And Emil will still wrap up this event. So yeah, thanks. Please, Emil.
All right, thank you very much, Tapio, for the presentation, and I also hope that people at the other side of the screens learn something. And if there are any questions, comments, just let us know via email or contact details that will be presented at the end of this presentation. Just shortly, Tapio discussed this area of a case of pulp, paper manufacturing, and like I said, that is because we are mostly working in that area, but there are other production environments as well. But what is common in all those where we bring most value with our expertise and solution is the same common goal or the problem is that there's too much variation in the process and quality in the operations. And the implications of that too much variation is that there might be, for example, too many quality defects and related waste, too many quality claims and related costs, too much raw material consumption, too much energy consumption, all kinds of things that prevent the mill or the factory from performing as good as it could. And why is it usually difficult then to decrease variation is one of the key reasons are that the data is scattered in many mills. There are many different data sources that need to be utilized in order to get relevant information by combining information from other different sources. And usually the tools that are at the moment utilized in many mills, plants, or factories, they might not be suitable enough to cope with this type of scattered data environment, or they might be too complex for kind of any employees in the mill to utilize. And then if they are too complex, then you have maybe one or two people in the whole mill of 500 people who actually can dig deeper into data, get relevant information from there. And these kind of people usually end up being bottlenecks of having all kinds of data related needs on their table that other people from the mill give to them. Whereas we could have a look at the kind of new world where everyone can utilize data better than before, and then there would not be bottlenecks in the utilization of data either. And this is the same thing on having no time to identify root causes if there are only scarce resources available to do that. And sometimes also specific case, if there are mills who have a high number of products or grades of a product that are being produced, those also add up to the difficulty of getting rid of too much variation in the process and quality. So this is the typical environment, regardless the industry in which we're working with, that we are focusing on. And we have developed this Quva Flow software solution, which is enabling more stable production. And what is kind of key elements there is the automated refining of the information, the analytics itself, and the visualization of the data there is already existing in the mill, and giving it in the format for the personnel who can do things with that, who can make better decisions based on that information. And in addition to that, the data comes from many different data sources in order to really understand the whole area in which the personnel should be working in. Here's just a short graph on how our system software looks like. And I'm not going to go into more details, but we combine the data sources, we configure the analytics engine, and then we visualize the information in the format which brings on-time information for the relevant people in the mill. So that's just shortly about our product, on top of what Tapio told about this kind of roadmap, how mills can evolve from having a very simple and straightforward approach to data quality assurance, and moving on step by step into more comprehensive approach, which utilizes more data but doesn't get too complex when the analytics and visualization is done in the way that it kind of takes away the complexity instead of adding more to it. So that's all about the webinar. Feel free also to visit our qvaflow.com, where you can download the free guide to data-driven manufacturing excellence. And also, if you're interested to hear more about our product or what we're doing, or you have any questions, comments, let me know. There are my contact details, and let's talk more. And you will be getting, as said already, you will be getting I'll just put a video here as well. So you will be getting the replay of the whole webinar 24 hours from now, and you can have a watch again if there's something you want to take a look again, or you can forward it to your colleagues and let them watch. Thank you very much for listening, and happy Christmas time when it's arriving soon. All right. Thank you.
Thanks.
Bye now.